Hello everyone, and in this video, we're going to be talking about a technique that can one-line this USAJMO problem, shown here. And it's a problem 5, so this will be really interesting. So here's the problem. Suppose you have a circle and a point P here, and you draw the tangents from P to the circle. We call them B and D. Then you draw any line through P, let it intersect the circle at A and C. Then you draw E such that D and E is parallel to AC. And what we want to prove is that if BE intersects AC at M, then AN equals MC. This is what we want to prove. And in this video, we're going to be exploring a technique that will one-line this problem. You'll solve it in only one line. So what is this technique, you may ask? Well, it's called projective geometry. So I spelled it on a screen. It's projective geometry. So what is projective geometry? Well, the basis of it lies on this fact here and definition. You have some points A, B, X, and Y on the line. Then we define this new thing, A, B, semicolon, X, Y. We define it as XA over XB divided by YA over YB. And it's plus or minus this entire thing. And it's plus if the segments intersect. Actually, it's minus when the segments intersect, and then plus otherwise. So in this case, the cross ratio ABXY is negative. Oh yeah, this is called a cross ratio, by the way. So what is so special about this cross ratio quantity? Well, let's go ahead and have our points A, B, X, and Y here. And then we have another point P here. So, and then we draw the lines PA, PX, PB, and PY. Now we want to look at the quantity. So we have XA over XB times YB, or divided by YA over YB. Now we want to look at the sine of angle XPA over the sine of angle XPB divided by the sine of angle YPA over the sine of angle YPB. And it turns out these are equal to each other. And this is the basis behind projective geometry. So how do we prove this? Well, the main factor we're going to use is called the law of sines. Because we have these opposite angles opposite to these sides on the line, so we're inspired to use the law of sines. So here we have that XA over the sine of angle XPA. By the law of sines, this is equal to AP over the sine of angle AXP. And then we have XB over the sine of angle XPB is equal to PB over the sine of angle PXB. Thus, whenever we divide these two, since sine of AXP is equal to sine of BXP here, we get that this is just equal to XA over XB times sine of angle XPB over sine of angle XPA is just equal to AP over PB. And therefore, sine of angle XPA over the sine of angle XPB is equal to XA times PB times XB times AP. Similarly, we have that the sine of angle YPA over the sine of angle YPB is equal to YA times PB over YB times AP times PA. Now we can take the ratio of these. If we divide one by the other, we get that the desired quantity we want, the sine quantity. This is just this quantity here. This is equal to the new. Well, we have the PVs cancel out and the ABs cancel out, so we indeed get what we want: XA over XB divided by YA over YB. So therefore, we prove that these quantities are equal. What does this mean? The significance of this is that we actually have cross ratios of lines now. So if we have a point P here, and then some lines here with A. That's not a good location for the point A. Then you have these lines here, and then you have A, B, X, and Y, and then you have these points A prime, X prime, B prime, and Y prime. Then the cross ratio AB XY, it's actually equal to A prime B prime X prime Y prime. This is a key fact. This is really important because now we can project from one line to another. We can project cross ratios, hence the name projective geometry. Oh, and because we have cross ratios between lines, we can have cross ratios of points on a circle. So if we have A, B, X, Y, then the cross ratio A, B, X, Y for points on a circle, if you have a point P here, then you draw these lines here, then that means that it's equal to just the cross ratio of these lines, the PA, PX, PB, PY. And it's constant for any point P on the circle by the inscribed angle theorem. And now let's get to the most important type of cross ratio, called a harmonic bundle. So a harmonic bundle are points such that AB, X, Y is equal to -1. So if we have point A, B, then X, then maybe Y here, then this is a harmonic bundle. What's so special about harmonic bundles? Well, let's look at what happens when we have harmonic bundles on a circle. So we have A, B, and then X, and then Y here, suppose. We want to explore when this harmonic bundle A, B, X, Y is equal to -1. And it turns out, if you extend the tangents at X and Y, then the point, and they intersect at the point Z, then Z, A, and B are collinear. They all lie on the same line. If and only if the cross ratio AB, X, Y is equal to -1. So how can we go ahead and prove this? Well, now we have that. We want to show that the cross ratio AB, X, Y is -1 in the case of the tangents thing. So we have the cross ratio AB, X, and Y, and we can project from circles to lines from points on the same circle. And this is equal to the cross ratio. If we project onto the line, we say we're projecting at X. We denote the superscript on the equal sign. Then if we project through X onto the line ZB, then the point A gets mapped to itself, the point B gets mapped to itself, the point X gets mapped to, because In the long term, like in the short term, if we have a point P here, then we're going to have it there, get even closer, we're going to approach the tangent. So we just extend the tangent in x, and that hits at z. So z and then y gets sent to the intersection w, zw. On the other hand, what happens if we project through y? Well, then a, b, x, and y is equal to, when we project through y, a, b, and then x goes to w, and then z. And it turns out that the condition a, b, z, w equals a, b, w, z is enough to imply harmonic. And to see why, let's take the definition. We have za over zb times wb over wa is equal to wa times zb over wb times za. And hence these are inverses of each other. So one of them must, so either they're both equal to 1 or they're both equal to -1. I should add that the cross ratio equals 1. So it's plus or minus 1. So in the case that they're overlapping, it must be harmonic. And because they are overlapping, this means that it's equal to -1. And therefore, this cross ratio ABXY is equal to -1. And one final thing we need in order to solve the JMO problem is that if we have A and B, then if we have the midpoint M of BC, of AB, sorry, we want to find out the point on a line AB such that ABMP is equal to -1. And it turns out P doesn't exist in a sense. But we can make it exist if we go to the very end of the line, like very end, we have a point P infinity. It's at the very end. And it's pretty easy to show that ABM P infinity is equal to -1. And we can use a point P infinity if we have two parallel lines. The two parallel lines intersect at P infinity. All right. With all that said, let's get to solving the problem. So now we bracket our JMO problem here, and we want to show that M is the midpoint of AC, given that DE is parallel to AC, and PB and PD are tangent to the circle, and PA and C are collinear. Well, given the projective geometry, this should immediately ring a bell, that ACBD is equal to -1, because ABCD is harmonic, as we just discussed. So we know we're going to use some cross ratios here. How can we relate cross ratios to the midpoint condition? Well, we have this midpoint condition here. So M is a midpoint is equivalent to AC M, and then the point at infinity along the line AC, the end of the line, is equal to -1. Now, where could we project in order to make this cross ratio equal to this one? Well, the point A needs to stay as is, as does the point C. And the point B must get to the point M, and the point D must get to the point P infinity. So there's only one other point on the line BM, which is Z. So we might want to think of projecting at E. So we want to show that ED and PC intersect at this P infinity, the point at infinity. But the two parallel lines, they intersect at the end of the line, which is P infinity. So here's our one-line solution as promised. It is just ACMP infinity is equal to, when projecting through E, ACBD And we know this is given equal to -1 by the given 10 conditions. And here's our promised one-line solution. Here we go. A JMO problem 5 solved in one line using projective geometry. Really cool, right? In another video, I'm going to be discussing the nice problem that extends on this idea and solves another problem in a similar fashion. So thank you so much for watching. I hope you enjoyed.